And we're back. Okay. This is example one as mentioned. So here, this is the same problem where we left off. I hope you tried this on your own first. Anyway, if you're watching this without trying it first, that's fine. So I'd like to show you the solution for this problem, at least using the procedures that we have in class. So this is your problem, and this is our analytical model. I took the liberty of naming the joints. This is joint 1, 2, and 3. This is member 1, member 2. Then we started off numbering the freedoms. Again, for each joint, you have 3 degrees of freedom. You have horizontal, vertical, and rotation. So you have 3 joints, so we have 9 freedoms in total. Uh, Take note first of the support freedoms. You have a support freedom here, vertical, and then on this end, since this is fixed, all of these are support freedoms. Now, we number first the relative degrees freedom. That's what we're used to. So I number this as 1. Start from joint 1. This is freedom 1 horizontal. Then the rotation is freedom 2. You move on to the next joint because that's a support freedom. So we move to joint 2. This becomes freedom 3. Vertical is freedom 4. Rotation is freedom 5. Okay, so we only have 5 relative degrees of freedom. So that's done. Then we move back again to joint 1. Then we number the support degrees freedom. So this becomes freedom 6. Freedom 2, no support freedom. Freedom 3, joint 2, no support freedom. Joint 3, so we start with the horizontal, that's freedom 7. Vertical, freedom 8. And then rotation is freedom 9. Okay, so that's our analytical model. It's just a matter of transforming the information into tables. So we first have here the joint coordinate table. You have 3 joints. Okay. I prefer using millimeter values in millimeter so that I don't confuse the units or the units for the answers. So we have here joint 1 coordinates would be 0 and 0 for x. Remember, this is our origin. The entire figure, the entire structure should be in the first quadrant. So this is our origin. The x coordinate of joint 1 would be 0 here. Then the y coordinate would be 6,000 millimeters or 6 meters here. Do the same for joint 2. That's 6,000, 6,000. Then for joint 3, 6,000 because it is 6 meters from the origin, and then 0 for the y. For the member incidence table, you have only 2 members, 1 and 2. So A joint would be the lower number joint, so that's joint 1. B joint is the higher number joint or the far end, so that's joint 2. Then for member 2, it's 2, 3. Okay. The destination table now, you need to list down all 6 freedoms per member. Okay. So again, A joint would be the near end, then B joint would be the far end. For member 1, look here. So the order should be 1, 6, 2, 1, 6, 2. Then for the far end, that's 3, 4, 5. 3, 4, 5. For member 2, you have 3, 4, 5 for the near end and 7, 8, 9 for the far end. So that's a destination table. Next, you need the member properties. It's a bit long, but you need all of these information anyways. So you list down the members. You have 2 members. You get delta x and delta y. So again, it's just a matter of subtracting the x coordinate of the far end and the near end joint. So I'll show you the formula. It's something like this. As you subtract these 2 to get that value. Okay, for delta y, you subtract these 2. So that's for member 1. Okay. Now you do the same for member 2, then you get L. So again, L is just the square root of the sum of squares, Pythagorean theorem. Then you also need cosine theta. So again, that's delta x over L. Then you have sine theta. That's delta y over L. Okay. The area is given in square millimeters here, here. I is also given, E is also given. So I is already in millimeters. You just need to convert GPA to MPA. We prefer MPA because uh, that directly corresponds to Newton per millimeter squared. Okay, so we have here A 600 for both members. E is given as 200 GPA, so I converted it to MPA, so that's 200,000. Then you compute for AE over L using these values. So just divide um, the product of A and E by L. That's easy. I is here also. I convert. This is 60 times 10 to the 6th. Yeah. Okay. Then you compute for these values. 12 EI over L cube. Okay. Then 6 EI over L squared. 4 EI over L and 2 EI over L. Do the same for member number 2. So after setting up all of the information, you can now start computing for the global member stiffness. So you'll be needing the local member stiffness for each member. Take note again, this is a 6 by 6 matrix. The formula would be what we discussed in the last lecture video. So I placed here the destination along the column header and the destination along the row header here. So that's 1, 6, 2, 3, 4, 5. Okay. So this matrix, okay. So the mic got cut off, so I'm recording this again. So here, these are the values that you need to get from the table. Again, we're only using 5 of them because the other values here, for example, this negative 20,000, will be sourced from this one. So you just link this with or from this. Okay, now we move on to your transformation matrix. You just need these two values. This is cosine theta, this is sine theta. Then this is negative sine theta. So you just get this value from that one. Okay. Then this one you get from here. This is 0, 0. This is 1, 0, 0. So again, this partial matrix would be the same as the one here at the bottom right. Okay. So as you can see here, it's just a matter of these values. Okay. Just link all of them, okay, to the upper left matrix. Then the rest would be zeros. Okay, here and here. Okay. Now to get K1G, you do need to, perform the operation. You multiply twice. Okay, first you multiply H and K1L. Then you multiply that product by the inverse of H. So it's a double multiplication step, similar to what you did for trust members. Okay, so now you have your global member stiffness matrix. Now you also need to create your local member fixed end reactions. Take note that for frame analysis, we do have local and global member fixed end reactions. In the previous example for beams, we only have member fixed end reactions. That's because for beams, at least the ones that we analyzed, all the beams were horizontal. Okay, so there's practically no local or sorry, the local axes are the same as the global axis. Okay, so for the local member fixed end reactions, you need to analyze each member by span. Then get the fixed end moments and the fixed end reactions, then you list them down here. Okay. So since our problem, doesn't have any load along the span, so that should be 0. The fixed end reactions should be 0 for both members. The 5 kilonewton here will be part of the nodal loads, okay? Nodal loads, not exactly part of the fixed end reactions. I hope that's clear. Okay, so this would all be a bunch of zeros. But I'm still including the step here because this is the general procedure. Okay. Now to get your global member fixed end reactions, PFMG, you just multiply this PFML by H. So we're just transforming them from local to global. So I'd like to show you that here. Click here. Okay, so we're just multiplying this matrix and this matrix. Now you do the same for member 2. Okay, take note you need to change the destinations correspondingly here as well, here as well. Then you're done with the stiffnesses. Now you need to assemble the structure stiffness matrix KRR because you will be needing this. The size would be R by R. So since we have 5 relative degrees of freedom, the size would be 5 by 5. So again, you assemble this from your KMG. Okay, you need to add all of the corresponding stiffnesses based on the destinations. Okay, so you know how to do that already. Now for the fixed end reactions, you get these, again you assemble these, or this array or this matrix from here, from PFMG. Okay, you assemble that from PFMG. Okay, you assemble fixed end reactions, PFR, from PFMG. Now for the nodal loads, you get these values from the analytical model. In this case, this one. You have 5 kilonewtons or 5,000 newtons along freedom 3. So that's along freedom 3, you put it there. That's positive because it's the same direction with the freedom. Now, you can get UMG, you now proceed to UR, yeah, this one. And you do this by following this formula. You first multiply the inverse of KRR to the difference of PR and PFR. Then you should get UR. Okay. Don't forget to indicate the appropriate units, millimeters, radians. Okay, that depends on the degrees freedom. So since freedom 1 is horizontal, that's in mm. Freedom 2 is rotation, that's in radians. Now from UR, you now assemble your UMG, global member displacements. You just follow the destination table as set here. Here. Okay. You do that for both members. Then you compute for PMG. The formula is given here. That's KMG times UMG plus PFMG. After getting these values, obviously these are quite large. This is very small. This is 0. I'd like to mention that the values here are in terms of Newton and millimeters. So when you do assemble your reactions, again, you just get these values from PMG here. We can convert them to kilonewtons, so that the values look better. So if you notice, these values would be the same with the ones in the slides. Okay, so I just divided this by 1000 so that I convert it to kilonewtons. Then this one I divide by 1000 squared, so that's in kilonewton meter. So we're done. Also, you need to draw your shear and moment diagram and your elastic curve, but that's up to you now. Okay, so that's example 1, and I'll leave example 2 to you. I'll be uploading this spreadsheet so you can have a reference and then practice on this problem. So that's where we end. I hope everyone's good and well, and we're still learning even though classes are suspended. So yeah, see you when classes resume and stay healthy.